So for today, we're going to be dealing with similar right triangles. And what you need to understand that if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles that are formed are similar to the original triangle as well as similar to each other. So you need to actually take a look at the fact that there happen to be three triangles here: a small triangle, a medium triangle, and then the large triangle. And if we rotate, translate, reflect all these triangles to make them all going in the same direction, you'll see that they're all going to be similar in that FJG is similar to GJH, which is similar to FGH. And this reason being is all of these guys are short legs of their particular right triangles. All of these guys are the longer legs of their particular right triangles, and all of these guys are the hypotenuses of their original right triangles. So that's how we're pairing them up: short legs, long legs, and hypotenuse. So what happens is we're going to be trying to find the missing sides of all of these, of this one big triangle. We're going to be trying to find the missing sides of it. So one of the theorems that we deal with is called the altitude theorem. And the altitude theorem happens to be where the measure of the altitude to the hypotenuse of a right triangle is the geometric mean of the length of the two segments that form the hypotenuse. Geometric mean is just a big word for has to be a cross product. They have to be on diagonals of a triangle, or of a proportion, excuse me. So what ends up happening is the altitude is CD in this case. So I'm going to call CDH, which stands for height or altitude. And I know that the hypotenuse of the big triangle is all of AB, but the two segments that form the hypotenuse are AD, which I'm going to call X, and DB, which I'm going to call Y. So what's happening now is this altitude is giving me two separate triangles. It's giving me a triangle here, the smaller triangle, and then a bigger triangle. So if I look at those triangles, especially if I look at triangle 1, and I pull out X and H, if I write X is to H, and I need to find the matching corresponding ratio, well, I realize that in that small triangle, X is my short leg, and H is my longer leg. So I have to be consistent when I work on the other triangle to say, all right, well, what's my short leg of my second triangle, the triangle on the right, and what's my long leg? Well, it turns out that my short leg of the triangle on the right is going to be H, and my long leg is going to be Y. And here's the proportion that you would use to find any of those missing sides. Go back to reading it again. The altitude is the geometric mean. Here's the geometric mean, it's the cross products between the length of the two segments that form the hypotenuse. Well, the two segments that form the hypotenuse are X and Y. It does not matter where those X and Y go. It could be Y on the first fraction, X on the second. It doesn't make a difference. The cross product, no matter what, is still going to be the same. Okay. Now we've got something called a leg theorem. And the leg theorem, oopsie, sorry about that. Oh, how do I get rid of that? I don't know. That's okay. So then we've got this leg theorem, okay? And again, it's still set up the same way. If you draw an altitude to a right triangle and then you get similar triangles, that the leg, each leg, becomes the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. That sounds kind of confusing. So here's what we're going to do. We're not worried about altitude theorem. I'm not labeling CD at all. But I'm going to keep my part of the hypotenuse as two parts. AD is the X part, DB is the Y part. And I'm going to call this leg on the left line segment AC. I'm going to call that leg A. And I'm going to call line segment CB leg B. If I take a look at, actually, I'm going to erase B for 1 second. If I just keep leg A, I see that leg A is a part of two triangles. I keep doing this. Let me see how I undo that. Okay, so leg A is a part of this small triangle, and leg A is also a part of this big triangle. So we've got two triangles that we're working with. So I'm going to just take a look at the yellow highlighted triangle, and I'm just going to pull out the two sides A and X. Okay, so I've got A is to X. Well, I know that in that small triangle, A acts as the hypotenuse. X acts as the short leg. So when I look in the green triangle, highlighted green, I've got to find the hypotenuse and the short leg again. Well, in the green highlighted triangle, my hypotenuse are the two segments, X and Y, together that form line segment AB. So it's X plus Y is the hypotenuse. And the short leg of the highlighted green is A. So here's my setup now. Again, it says to you that the leg is the geometric mean. Okay, well here's the geometric mean. It's on a diagonal between the entire hypotenuse and the part of the hypotenuse attached to that leg. Now let me introduce the other leg. Hello leg. So here's the other leg. So B. Now we're going to talk about the B leg. Now the B leg is definitely a part of what's highlighted in green, but then the B leg also is a part of what's highlighted in blue. So if I just deal with the B leg, I'm going to have a proportion like this. I'll talk about blue, highlight, B, and Y. Well, in the blue highlight, B happens to be the hypotenuse. Y happens to be the long leg. So when I go to the green triangle and I look for hypotenuse and long leg, in the green highlighted triangle, the hypotenuse is X plus Y, and the long leg is just Y. And again, if I go back to the words, I did something wrong here. Sorry, and my long leg here is just B. Something didn't seem right here. Here we go. So we've got now, if I go back to the words, that the leg B is the geometric mean between the whole hypotenuse, X plus Y, and the part of the hypotenuse attached to that leg B, which is just Y. So those then are your two proportions that you need to have for the leg theorem. Let's do some math here. We've got some radicals that we've got to deal with. Okay, so we want to simplify radical answers, so we don't want decimals. You can use a calculator, but no decimals are allowed. We've got the altitude CD drawn to hypotenuse AB. We've got a right triangle. They're telling you that AD is 6 and DB is 24. They want you to find this altitude. This is the altitude theorem where I know that my altitude is going to be the geometric mean between the two parts of the hypotenuse. Because again, if I deal with this triangle here, then my altitude, my height is long leg, my 6 is the short leg. If I now look at this triangle here, my 24 is my long leg, and the H is my short leg. You saw proportions by cross multiplying. H squared equals 144. What's H going to be? And that's where you have to square root both sides, and H is just 12. 144 is a perfect square. If you've got the calculator, life is good. Let's try this next one. Now we're looking for 6 and 24. Now we're looking for AC, which happens to be this leg on this side. And this goes to the leg theorem. So I know that the leg is to its particular part of the hypotenuse attached to it, as the whole hypotenuse is to that leg again. In other words, we're doing this separate triangles, where I'm dealing with this guy right here and this guy right here. So what's happening on this first triangle in the blue is I've got hypotenuse from blue and short leg from blue. And from yellow, I've got hypotenuse from yellow and short leg from yellow. Now when I cross multiply, I'm going to get A squared equals 180. Well, as it turns out, I can't square root 180. It's not a perfect square, but I can simplify it. So here's where you need to figure out how you guys did your square roots. But for me, I'm looking for the largest perfect square that divides into 180. And I know perfect squares, if I count by them, 1 squared is 1, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. I think you're following me. 7, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, 13 squared, so on, so on. The way that I teach radicals is I look for the largest perfect square that divides evenly into 180. You've got a calculator, should make it a lot easier for you. And I know that 180 is divisible by 36. So I know that I can break down 180 into 36 times 5. I know the square root of 36 is just 6. Square root of 5 is irrational. And here's your answer for that leg, 6 root 5. If you don't know how to do it that way, then you got to worry about the factor trees. And factor trees would look like this. I'm not sure who taught you last year, but if they taught you factor trees, this would be something like 9 times 20, 3 times 3 times 3, 4 times 5, 2 times 2. And the factor trees work this way, that I've got a pair of 3s and I've got a pair of 2s, which means for my final answer, I've got a pair of 3s, I've got one pair of 2s, and a 5 that was not used, and this becomes 6 root 5. Again, not sure how you do square roots. I don't like the factor trees as much as I like it the way that I did it with the largest perfect square. Let's get the last one done. We still have 6 and 24. And now we're looking for CB, which is Y. And again, if you think about the triangles that you're dealing with this little triangle here, and then the whole big triangle. So what's going to happen for your proportion is you could say, yellow triangle, Y is to 24. Okay, it's going to be hypotenuse is to long leg, as hypotenuse, big triangle in blue, is to long leg. And then when you cross multiply, excuse me, you get y squared equals 720. And the way that I do my square roots is to find out what the largest perfect square that divides evenly. It turns out that it's 144, and that's multiplied by 5. That's the same thing as 720. Well, the square root of 144 is just 12. So the answer is 12 root 5. Again, if you want to do a factor tree on 720, here's the way you can do that. 720, 9 times 80, 3 times 3, 10 times 8, 5 times 2, 4 times 2, 2 times 2. So I've got one pair of 3s, so that's going to come on the outside. I've got a pair of 2s, so that's going to come on the outside. I've got, this doesn't count anymore, I've got another pair of 2s, so that's going to come on the outside, and I can't do anything with that 5, so this becomes, again, 12 radical 5. All right, there you go. Good luck.